Okay, so today we are starting 13.7, which is, this is a very heavy, very dense section, all right? There's a lot in this. I've put up the solutions for homework for 13.6 as of yesterday. I've started to put up homework solutions for 13.7. If for any reason any of you came by my office this morning, I was not there from 9 to 11. I apologize about that. I had something come up. So let's start off 13.7, which is called surface integrals. All right, that's what this section's called, surface integrals. And what I thought I would do is summarize where we've been in terms of integration partially in this class. We've done double integrals, triple integrals, but if you look at all the integration that we've done where we have scalar functions, all right, where back in Cal 2, you did, you had a function, a scalar function, f of x, and it was defined on some interval a, b, and we wanted to find the area underneath this, right? And so this was the formula for it. And the dx represented the infinitesimal width of a little rectangle that we were going to put in there, and then we're going to add them all up. That's what this was, right? Good? Then we learned that we can do these things called line integrals in this chapter, which is just a slight adaptation of this, where your curve, instead of your curve being a straight line segment on the xy plane, we can actually allow that curve to move around anywhere we want in the xy plane. And we define this line integral to be the integral over the curve C of the scalar function f of xy. Now it has two variables because you have to know the x and y coordinates at each point. And with respect to, anyone remember what that was? ds? Arc length, right? So this little ds was this little infinitesimal arc length that we got from here, right? And what we did to draw the curve is we came out with parametric equations, which we drew it with a vector function, r of t. We put restrictions on t, and then this integral turned into this. So it's like the x gets replaced with the x function, the y got replaced with the y function, and then this right here, square root of the sum of the partial derivatives squared, right, is just the arc length. So this right here is just ds, right? Then what we did is we said, okay, what if this curve lives in three-dimensional space? So you have an x, y, and z coordinate for each point. Then we can do the same sort of line integral over a scalar function of three variables now. We still want to do it with respect to arc length, so that's a little arc length right there. We still come up with a vector curve that draws it, but it's three-dimensional instead of two-dimensional, right? 1, 2, 3 components for the vector. And then what we did is we tweaked the formula a little bit using vector notation. And this was just plugging in each of those component functions into the scalar function. And this right here was our d little s, right? Okay, today, here's what we're going to do. We're going to have a scalar function. I'm going to want to do an integral. I'm just going to put it right here. We're going to be doing a scalar function again of three variables. I want to integrate it, but this time the domain, which I should have said here, this curve is like the domain of our integration. This curve is the domain of our integration. Here, this line segment was the domain of our integration, right? This time, the domain of our integration, we want it to be a surface S in three-dimensional space, all right? So it's just this thing floating around in space. It could be, a sphere. It could be a paraboloid. It could be a lot of things. It could be a plane. But it's a three-dimensional surface, right? This is our domain of integration. If I want to integrate a scalar function on that domain, then it's actually going to become a double integral over S. Okay, this is the way we write it. With respect to, and this is the big difference today, instead of looking at a little infinitesimal piece of the curve, I need to look at a little infinitesimal piece of the surface. So that would be some little infinitesimal piece here, which I will call d capital S. And capital S here stands for surface area. So we were integrating here, this little d little s, that was with respect to arc length. Now we're integrating with respect to surface area. So we're taking like a little infinitesimal patch and finding its area. And that's this part, understand? So that's d capital S. And by definition, I'm going to put this on the board in a second, what this turns into is the double integral over d of f of something and then the cross product of the partials dA. So let me explain what this is. Let me just go ahead and put what's in here, r of uv. So what was r of uv from the last class and maybe the class before? What does a vector function of two variables draw? A surface, right? So what we're going to do is we're going to be plugging the points of the surface into our scalar function, right? That's what this means. This right here should be ds. And do you remember what the magnitude of the cross product of the partial derivatives of our vector surface represents? That times this? If you look at last class, we actually did a double integral over S of just that. Yes, what is this double integral right here? Just without that f thing in front. What is the double integral right there? That's the surface area of our surface, right? So that little piece in the back is our ds now, all right? So one way you could look at this is, do you remember this formula? Do you remember the formula double integral over d of 1 dA? Do you remember what that represents? The area of the region D, right? That's what that is. If I make this right here a 1, right? Or I should put it here. If I make this a 1, then this should just be the what? Surface area of the surface, right? If ds is this, then that becomes that formula. Do you see that? Now what we're doing is we're not allowing this to be a 1, we're allowing that to be a scalar function. Now we cannot visualize like what this is. It's not the area of a curtain like it was over there. Like over here, remember this was the area of a curtain. Over here we lost our ability to visualize it. And for here we definitely lose the ability also. Okay? You all right with this? All right, that's where we're headed today. We want to just do basic surface integrals. I'm going to put the formula up here from the notes. Given a scalar function f on a surface S with a vector equation given by r of uv with u and v and d, then here is the formula. So this is the surface integral, which turns into a double integral over d of this with respect to area. And d here, our restrictions are on u and v. All right, whatever our restrictions on u and v are going to become our limits of integration on this double integral. I think we'll just get right into an example. Find the surface integral over the surface S, x, y, z, with respect to surface area of the part of the unit sphere above the cone z equals square root of x squared plus y squared. Pardon me?
Should we even try to draw it?
Yeah, I'm going to try and draw it. Let's see if we can. Yeah. Well, I have a unit sphere, right? My surface S is part of this unit sphere, right? So here's my unit sphere. But it's only the part of the unit sphere that is above this cone. z equals the square root of x squared plus y squared. Now you have to remember what that looks like when we studied these way back in chapter 10. I can get some points pretty quickly if I let x and y be 0, z is 0, right? So the origin there. And then what if y is 0? What if y is 0? This turns into z equals x, or the absolute value of x, right? Which would look like a v. So along one axis, or along one plane, when y is 0, you're looking at the xz plane. You should have a v, and then if you let x be 0, you should get the same thing, right? So it's going to look like there's your cone, right? Understand? So we're looking at where this cone punches out of the sphere. It should create this little cap up here, shouldn't it? And that right there is our S. Yeah? So what now? Yeah, we need to come up with, we actually need to find now some vector function, r of uv, that will draw just that cap for me. Not the whole sphere, just the cap. So how do you want to draw that cap? How would you draw the sphere if I asked you to draw the sphere? Okay, so you would use the spherical coordinates formulas, right? All right, so let's see. If we did the whole sphere, and let's use u and v. Let's not use what were we using before u and v? Theta and phi. Let's just go to u and v now. I've used two different formulas. I did one on my paper and one in class. So I want to stick with what we used last time. Did I say cosine u sine v, or did I say cosine v sine u? Cosine u, no. Cosine v sine u is what I used in class, right? Now, I actually have a 1 out here, right? Because it's a unit sphere. And then what? Sine v sine u. And the last one, 2? No. Should just be. Cosine u. Okay. Want to make sure we're all. You all understand where that comes from? Okay. What are the restrictions that you put on v and on u to draw the whole sphere? Again, that's not what we want, but just so we're all on the same page, what would you put the restrictions as to draw the whole sphere? 0 pi for u, 0 2 pi for v. Now, if you remember, back from when we did spherical coordinates, this was like the phi, and this was like the theta, wasn't it? And do you remember how it works with spherical? You start at the origin, right? You're looking straight up the z-axis. Phi was this angle. Theta was your rotation this way, right? And rho was how far you go out. We know rho is 1. If I want to draw just this top cap, how much am I going to let phi move by? Well, whatever it takes to start here and swing down through there, right? I need to figure out what that angle is. What about theta? How far around do I want to go? All the way around, right? So I still want this to be between 0 and 2 pi, but I want my phi to be between, I'm saying phi, you understand you? I want that to be between that and something. Understand? So I need to figure out what this angle is. The angle, if you look at an angle straight up here, the angle that goes right there, that's u, right? That's my top restriction on u. So how would you recommend we do that? Okay, good. How about, yeah, we just draw a cross section. Isn't that a cross section, two-dimensional cross section right through the center of the sphere? Cut it open, look at it. That's what you would see. I'm trying to figure out what this angle is right here. I don't like calling it U because it's not really U. U is going to vary. Can I just call it like U tilde so it's something different? U tilde, is that all right? What do you know about any of this here? If I've cut it in half,
We know it's each of those is 60.
how do you know it's 60?
So cutting it into 3 equal pieces.
How do you know it's 3 equal pieces?
Then we cover them when we're drawing the skull with the cone right there.
Because when you cone, you got absolute value of x for one of them.
Yeah, okay, so look, when we cut it in half, think about it this way. I'm going to run out of the ability to show this.
Since that dotted line, which is isn't that bisecting?
Yes, it's cutting this in half, but I don't know what this is. I don't know if these are all equal,
Oh,
right? I don't know. Here, look, this is my three-dimensional, right? This is x, y, z. My sphere is in here, right? I've got my cone coming up out of it. If I decide to cut it right down here, right, and open it up, I'm really looking where x is what? 0. I'd like for us to just imagine then that this is the y-axis here, and this is the z-axis here, right? X is 0. If x is 0, what's the equation of this? If x is 0, that's the equation there is z equals the absolute value of y, right? That would draw this. Agreed? Y'all know why it's absolute value of y? Square root of y squared is the absolute value of y. I know a lot of times when we're doing algebra, we just say that that's y, but the only way that's ever true is if y was, well, y could be both positive and negative here. You get the same answer because you're squaring it. So we say absolute value, but okay. If that's z is the absolute value of y, then this part of the line is actually z equals y, and the other line is z equals negative y, correct? And z equals y means that this line goes out 1, up 1, right? Out 2, up 2, because the z and the y coordinates are the same. So the ratio here is the same. And I know that this distance is 1, don't I? That right there is 1. And I know that these two, whatever they are, have to be the same, which means it's a 45-degree angle, right? Agreed? This is 45, which means this must be 45 degrees also, right? So let's not use degrees, let's use radians. So 45 degrees is pi over 4. So I want my upper restriction to be pi over 4. Do you understand? Had they given you a different cone equation, you would have to go through this same process and try and figure out what that angle was. And it may not be so easy. You might actually have to determine, using like trig, sine, cosine, arctangent, maybe to get an angle.
Wouldn't it only be half of pi over 4?
What did I put? Pi over 4. Oh, yes. This is, sorry, this right here, just this. Hold on. No, hold on. No, this is pi over 4. Because look, this is 90 degrees, right? That's 90. So that's 45. That has to be 45. All right, we good? Questions? All we have done is come up with the R that draws the surface. That's it. Now what I need to do is remind myself what the formula is. This, I need to take F and evaluate it at the surface, and then I need to do this cross product partial derivative thingy, and then actually this is going to turn into D now because I'm actually going to go dA here. As soon as you put this in here, you convert it over to D. All right, do we know our restrictions for D? Like, Are we going to know these now? Yeah, we know what they are. How about we do some partials and crosses? Didn't we do that already last class? Did we do the partials and cross product of the unit sphere? We did. Let's save ourselves a little bit of time. What do you get when what did we get when we did this? Anyone? I think we got sine V. Will you go look?
We got, yeah, we got.
Or was it sine U? Sorry, I switched my U and my V on my work.
A squared.
Yes, a squared, but our sphere is. If you look at, you're looking at the other example. The one before that was a unit sphere. So we got sine U. If you go through the work, okay. So we're saving do you understand how much time we just saved ourselves, right? Okay. All right, so now we go and plug in to our scalar function the surface. So our scalar function is x times y times z, which means I'm going to take the x component of my surface times the y component of my surface times the z component of my surface. Then multiply that times this dA. So I have cosine v sine u, sine v sine u, cosine u, that's x, y, z, then sine u, then dA. And we can combine things together, right? Do I have any questions? Double integral. Let's see. Let's get all our u stuff together. Looks like I've got a sine cubed u, right? And a cosine u. That takes care of this, 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 and this. And then I have sine v cosine v or cosine v sine v. It doesn't matter how I do that, right? dA. You know, let's not do dA. Let's actually go to our limits. So we're going to have dv du or du dv. It's your choice. It doesn't matter because they're constants, right? Trapped between constants. So I'll do the v on the outer one, 0 to pi, 0 to pi over 4 here. And in that case, I've got to go du, then dv, right? And now at this point, I mean, we kind of know what we have to do, right? I'm also going to notice here that all my stuff with u's in it can be separated from all my stuff with v's, right? And when that happens, we can split this into two integrals and multiply those two answers together. So I'm just going to do it just to show off that we know what we're doing, right? We're going to be like, okay, I know this is just 0 to 2 pi. Let's see. That's my v's, right? So let me get all my v's in one integral. Sine v cosine v dv times, not plus, right? Integral 0 to pi over 4, and then all my u's. Sine cubed u cosine u du. Those should be pretty clean antiderivatives. Do you agree with that? This is a basic sub. Let u be sine v. Well, we shouldn't use u, but you let that be your substitution. The derivative of it's right there. So you should get, as an antiderivative here, 1/2 sine squared v. You're evaluating that 0 to 2 pi. Times, I already know my answer is 0. Right? What's sine of 2 pi? 0. 0, sine of 0, 0. This is all going to be 0, isn't it? It's going to 0 this out. But this one here, just again, we can just show that we know what we're doing. This is 1/4 sine to the 4th u, evaluated 0 to pi over 4. This one would not have given you a 0, right? You plug in pi over 4, figure it out. But since that first one zeroes out, I'm done. The answer is 0. Okay, so what does this answer represent? It is not the surface area of this surface. It's the surface integral. So here's the only way I can here's the only real way I can kind of get you to think of this. Imagine on that little cap that at each point on that cap it had a temperature. And the temperature was exactly the x coordinate times the y coordinate times the z coordinate. Let's just say that's what it was. Then this integral represents like your net temperature. And the net temperature here would be 0. So there's some positive and some negative, and it's kind of wiping each other out, and you just get a net of 0. That make sense?
But only on the surface.
Only on that cap. Only on that little piece. And it could be, you could have anything up there. No, you couldn't do mass. That wouldn't work because you'd have to have negative densities up there. Magnetic field, well, we don't want, fields are different. That's the next part of this section, is what if we're on that cap inside a vector field? Then you have basically like some sort of what we call flux. All right, we have like a flow through this surface. And we're measuring that, and that's what the flux is. So that's the difference between having a field versus having a scalar function. A scalar function is more like temperature. Temperature at each a value at each point, right? Temperature is this at that point. Temperature is this at that point. A field would be, at this point, we have a vector in some direction with some length. And at this point, a vector in some direction with some length. That's the difference. Got it?
Got it.
Okay. All right, let's see what the next one is. All right, a couple of applications of this. By the way, I believe that's the only example I'm going to give of a surface integral. In the homework, I do a bunch of other ones, but that just gets you kind of going, all right? Oh, wait, no, I think I do one more. Someone can look at notes. I think I do one more, because we've got some special cases we have to look at. But here are some formulas. I'm not going to give you an example of these. I think you've noticed, hopefully you've noticed, that in one of the exams I gave you, you had to calculate center of mass in moments of inertia for a problem a couple of mini exams ago. It was real tedious. Then the last mini exam, I asked you to find the mass in the center of mass of a wire, which I never gave you a formula for. But the formula does exist in the book. For this, I'm going to give you the formula, all right? That's a big hint, that if you're having trouble with that wire mass problem, it's because the formula, you have to actually read the book a little bit, all right? So what if we have a sheet, right? A surface, not a sheet, but a surface, and we want to know its mass in center of mass? Then if we know its density function, so we know the density of the material at each point, then we can do a mass by doing the surface integral, right? So that's exactly like the F was, right? I'm looking at the density at each point, and I'm adding them all up, and I get my mass. And then to get x bar, we do this. To get y bar, we get this. And then to get z bar, we do this. So this is all just extending off of things we've done. And so really, what we have in summary for calculus, right? I always want to erase that. It's not ever going to come off. We can find the density of a flat region, a lamina is what we called it, even if the density of that lamina is non-uniform. And to do that, we use double integrals. We can find the center of mass of three-dimensional objects, right? Using triple integrals. We can find the center of mass of a wire, assuming that wire, we're assuming that the wire doesn't really have width to it, which is kind of weird, and we could argue about that. We can find the center of mass of that. And now we're saying if you have a three-dimensional surface, you can find the center of mass. And again, we could argue about that. How can you have a surface that doesn't have thickness to it? If it has thickness, then isn't it a solid? Isn't it? Three-dimensional solid? All right. But we can we can kind of get away with that if it's thin enough, I guess. All right, next. All right, we have a special case when we're doing surface integrals. In fact, there's 3 special cases. I'm only showing one here in the notes, but I'll write down the other special cases. And here's what it's saying. Let's say that your surface is actually easy to write. In other words, you can write it as a function of 2 variables. When we first started chapter 11, I believe, we were looking at functions of several variables. And we said if you have a function f of x, y equals z, then that draws a surface, right? And the domain was the ground. If our surface can be drawn like that, then the formula we have for surface integrals becomes a lot easier to do. Now, the sphere we just did could not be done using this special case because you cannot write the equation of a sphere as a function of just 2 variables. You have to draw it with the vector function. So we couldn't. Understand? So one example of something we could use for this is, let's say we wanted to do just like part of that cone. Remember that cone? What if I just wanted to do like part of it? I could use this as the surface, right? And not ever have to come up with r of uv at all, okay? If that's the case, then this is what the formula turns out to be. Our x, which used to be the u, is just going to be itself. The y will just stay y, and the z will be the function of x and y. So what we'll do is, remember how in the previous problem we took the scalar function and we plugged in the vector function into it? Right? This time we're going to take the scalar function and replace x with x, replace y with y, and replace the z with the actual function of the 2 variables, which would have been like that cone, just the square root of x squared plus y squared. But then the magnitude of the cross product, this, if you do the computation of this, will always turn out to be this. Okay, so let's just look at what this is. Magnitude square root, right? 1 plus partial of this function with respect to x, partial of this function with respect to y, square them both. And what this shortcut allows you to do is not have to compute the magnitude of the cross product of the derivatives, because it will always turn out to be this. Always.
We had one just like this in 13.6, right?
Where
Where we did the